welcome you all to the SETI Institute here in Mountain View, California, and welcome Mark, welcome back.
Thank you, Bill.
From your very intense time. I was
intense is definitely a good word for it.
Following you guys on New Year's Eve, and you and me and Alan exchanged some emails even on the evening, which was very exciting. So anyway, this is an extraordinary mission, and what I think is really amazing is how long this mission took from launch. So maybe you could walk through, you know,
sure,
at a high level, the overall mission for our friends there out there in Facebook land.
Well, so even so, we launched in 2006. We put a very big rocket underneath a very relatively small spacecraft, about the size of a grand piano, and launched in 2006, going very fast. We crossed the orbit of the moon in 9 hours.
Wow.
Got to Jupiter in 13 months, and we had a very nice Jupiter flyby. And then spent the next 8 or so years crossing the solar system to get to Pluto in 2015, and now roughly 3 years, a little more than that, past Pluto, we have just done our flyby of a Kuiper Belt object, the most distant object, the coldest and oldest object that has ever been seen up close by human eyes.
So this is so Pluto, by the way, that's 3 billion miles away.
Yes, and now we're 4 billion miles.
And now 4 billion.
A little plus a little.
Oh, plus a little. So another billion
something.
miles and 3+ years to get to Ultima Thule from Pluto.
Yes.
And but actually, so when you mentioned Jupiter, so that flyby predates my being here with the Institute. Was there a lot of science done and observations?
Oh, absolutely.
On
in fact,
Jupiter on New Horizons.
I was an associate of the team for the Jupiter flyby. I was not a team member until something like 5 years ago.
Yeah.
But they needed some expertise on rings and satellites at Jupiter, and they invited me to join them, and I said, of course. And because of that, I was able to. Well, that came later. So we got the first movies of volcanism, active volcanism on an object outside the Earth. We got a couple of just short movies of volcanoes on Io.
Yes, those are extraordinary images.
And we did some beautiful imaging of the rings, which is what I focused on in my research. Got some close-up images of the red spot and other aspects of the clouds of Jupiter. It was a great flyby. And it was a great chance also to just test out all of our instruments, because that's one thing you always want to be able to do. Calibrate, for example. We've had other missions to Jupiter, so we kind of know how bright it's supposed to be, so you can do things like calibrate your instruments by looking at Jupiter with a new instrument.
Now, did Jupiter or any other planetary object serve as a gravity assist to?
No. Jupiter gave us a little bit of a fling, got us to Pluto about a year faster than we would have been able to otherwise. But now we're just cruising along at 14 kilometers a second. That's about 9 miles per second, and Pluto's got a pretty small gravity. Ultima Thule has a really small gravity, so they almost barely at all change the trajectory, and we're just cruising on out of the solar system now at that speed, and that's the final speed we're going to have.
Well, I think I mentioned this to you, but one of our mutual friends and I guess a former NASA colleague of Alan Stern's, John Morse, he and his son were at the launch of New Horizons. There's a picture with Alan and John's son. So Alan and John's son, and then they've done pictures since then at the Pluto flyby, and now most recently Ultima Thule, and now there's Alan and there's John's son. So it's a very graphic indication of just how long these missions take.
This mission isn't quite intergenerational. If it keeps going, it will become that.
It will become that.
But one of the reasons to send a small spacecraft on a big rocket is that you want to be able to get your scientists as quickly as possible, so that the people who planned the mission can actually reap the fruits and actually have the experience of knowing how the spacecraft operates. And so 9 years across the solar system is not a bad year.
It's amazing.
Not a bad rate.
No, that's not a bad rate. So we'll jump back to Pluto, but since New Horizons was the most recent, since Ultima Thule was the most recent flyby, why don't you talk a little bit about that mission, why it's interesting, who cares about a rock at the edge of the solar system, and why these are interesting objects?
Well, so it's a cold classical object in the Kuiper Belt. What that means is that it's been there for about 99.9% of the lifetime of the solar system.
So like 4.2 or more billion years?
Well, so if the Earth, if the solar system is 4.4 or something, whatever the number is, billion years old, just add a couple million years to that, and that's, or subtract a couple million years from that, and that's how long this object has been there.
And more or less unchanged. I mean,
exactly, and that's why it's so remarkable that you can see the little snowman here. This is the website, pluto.jhupl.edu. That's the official website for the flyby. So Ultima Thule, as we finally got close and saw it, is actually a contact binary. It is two almost spherical objects, almost identical in all the properties that we can see so far, just touching each other, barely touching. There's a very little neck of where they kind of mushed into each other a little bit. But so the fact that
suggests some sort of slow merging, not a violent contact.
It suggests a couple things. The fact that the two pieces are nearly spherical, and then afterward they must have touched very, very slowly, means that they probably formed out of the same cloud. Somehow or other, there was a little turbulence and some smaller particles came together, but when they do that, they form almost perfect spheres. And then as they interact, and perhaps there were other moons or were other moons out there, the whole system interacts such that the two central objects, the two largest, come together and touch, just very gently touch. And they've been that way for the last 4.4 billion years. They are still almost perfectly spherical. I mean, by planetary standards, they're not big enough to have their own gravity, so they're spherical because they formed that way. So far, we haven't seen any craters. So far, or at least anything we can be sure is a crater. So these things have just been there more or less as they were at the very beginning of the solar system.
So this thing, if I recall correctly, is about 20 miles, or is it 20 kilometers long?
The numbers I remember, it's a snowman. In fact, I brought my Pluto Karen along.
Yeah,
this was put out shortly after the Pluto flyby, and they have little magnetic connectors. But little did they know when they put out Pluto and Karen that if you connect them together, you get Ultima Thule.
That's actually
so
without the feet.
Without the feet, but this is my little. Well, there could be little protuberances we haven't seen yet, but this is my little visual aid for if I need to talk about Ultima Thule. But so the small one is 7 kilometers across, so that would be about 5 miles, 4 miles, and the bigger one is almost 10 miles across, so that would be. I'm sorry, I got that backwards. 7 would go to about 10 miles.
Yeah.
I'm sorry, no, 7 kilometers. No, so that would be 5 miles.
5 miles.
And 10 kilometers would be about 7 miles.
Yeah. Okay. Interesting. And about 20 kilometers.
Yeah. Well, they're just almost two spheres touching. So you add the 7 and the 10, you get 17, and that's just about the size in that dimension.
Yeah. Interesting. And so, why is an object unchanged over 4.4 billion years interesting?
Well, it's very far away from the sun. This is a contact binary. You can see that with a little magnet, but it's actually literally what scientists have long called a contact binary. Contact binaries are somewhat common in the solar system, but they're much closer in. We've seen cometary nuclei often look like contact binaries. We see asteroids, some asteroids that are contact binaries, but they've been shaken and baked by the sun for the entire history of their time in the solar system. So they are very, very eroded. They have very weird shapes. They have lots of craters. All these kinds of things. And so what we are seeing now is the prototype of the contact binary, which is essentially two perfect spheres far out in the solar system that have stayed there forever, whereas so many of these other objects have fallen in or got tossed around. But in any case, they're much more complicated shapes. This is like the perfect canonical idea of two spheres stuck together, and that's a kind of remarkable thing.
But we're also interested in their composition,
Oh, absolutely, and we don't have too much information on that yet. We know they're reddish, but we don't know, and that's a pretty common color for things. If you have a little bit of carbon or organic materials on the surface of any object in the solar system, it tends to turn red. It's fairly dark, just somewhere around 10% of the sunlight that hits it reflects it. So if we saw this on Earth, we would say, wow, that's really black. But in fact, it's a typical brightness for an object out in the solar system. And but we'll get some composition later. We get some spectral data that will start to tell us what is what on the surface. But right now, we only just have a limited number of images. We have a long wait to see the entire data set. It's going to take about 20 months to get it all to the ground.
Yeah. And that's on a, how long was the flyby? In other words, how long was that data
Well,
collection
okay,
period?
so Ultima Thule is about 14 kilometers long, and we're flying at 14 kilometers a second, so that would be about a second for the flyby. But in fact, we're doing, I would describe it as something like 12 hours of really core science, where we're approaching, we have a very good camera, the telescopic camera, so we were getting good images 12 hours out and 12 hours in the other direction. So we've got this kind of block of 12 or 24 hours where we've got our really best data. But that's what we'll be hoping to see very soon.
Yeah.
But a lot of it will take 20 months to come down.
That's just because the data pipeline is so limited.
Yes, that's right. And we have to share it with other NASA spacecraft as well.
Yeah.
But I will say this, now that we know exactly what the timing of the flyby was, we will be able to go in, our team will be able to go in and command the spacecraft to send down what we now retroactively know are the best images.
Oh, really?
And so sometime in, I think it is early February, we should actually see the highest quality images of Ultima Thule.
So how is it you have pre-knowledge, if you will, of what are the most interesting images?
Yeah, so we didn't know what's called the time of flight very accurately. So they put in an uncertainty that said, we're going to basically look in the direction of Ultima Thule, and we're just going to take image after image after image for about 300 seconds. And somewhere in there, we're pretty sure we're going to get Ultima Thule, and then we're going to get a lot of black space that might show moon, so we're still going to look at those images too, but mostly it's going to be black sky, but then we'll get some very good images of the object itself. And now that we've reconstructed the flyby retroactively, we know roughly when that flyby happened,
so
much better.
time.
So what we call the noodle, this long string of images, we can then command the spacecraft to say, go to these images, because these are the ones that probably captured it, and then we'll get those down in February.
And just to give everybody an idea, how long does it take that instruction to get to the spacecraft to say send these, and how long does it take to get back?
So, so of course you always have to have redundancy at NASA to be safe, but it's a 6-hour one-way light travel time.
Yeah.
So
that's the speed of light.
That's the speed
6
of light.
hours.
Yes, it is.
Just to the edge of our solar system.
So we send a command to the spacecraft to do something, and then we have to wait another 6 hours for it to come back down. So that's 12 hours. And if there was anything wrong with the acknowledgement that it didn't get the commands correctly, then we have to be able to send it again and wait for another reply. So really doing anything that involves communication with the spacecraft now takes 24 hours. Round trip twice.
Yeah, unbelievable. And so actually also the very existence of knowledge of the existence of the Kuiper Belt is fairly recent.
That goes back to the mid-90s, I believe.
Yeah.
I'm afraid I don't remember the exact date, but well, actually, to correct that, no, it goes back to 1931, because Clyde Tombaugh discovered Pluto. Here, and Pluto was basically a Kuiper Belt object. We didn't know it at the time. And as time went on, it became clear that it's quite a bit fundamentally different from many of the other planets. And in fact, it's the largest and innermost of the Kuiper Belt objects that we know of.
But it's basically
it is basically the discovery of the Kuiper Belt, and it was only in the 90s that we saw the second Kuiper Belt object.
But it was around that time, I guess in the 90s or maybe even a little later, that we realized that this belt was actually littered with material. I mean,
tens of thousands of objects.
Right.
Now. Yes, that's right. That's right.
That's
but it is it is the sort of the deep freezer chest of the solar system. It is where all the oldest pieces of the solar system are still there. So it's essentially like say you've been studying life on Earth as a paleontologist, and then you see for the first time a fossil of a trilobite. It's kind of like that. We're seeing the fossil. That something we've never seen before, because we've seen all the stuff that's around today, but now we're finally seeing something that goes all the way back to the beginning of the origin of the solar system.
This is space archaeology.
It could be space paleontology or space paleontology, something like that. Sure.
And it's like time travel, essentially, right?
It
You're
is
going back in time.
We are seeing something that is very, very 99.9% of the solar system has gone by since this object formed.
Right. And so we would hope, among other things, that part of the science coming out of this informs us about the process of planetary or solar system development, the development of the planets.
Exactly right. And the fact that our first object, the only Kuiper Belt object we've ever seen, is a perfect contact binary that clearly formed out of some swarm of smaller objects, because the two pieces are spheres, and that's the only way to make them spheres when they're that tiny. That's basically telling us what the environment was like early in the formation of the solar system.
Fantastic. And so possibly, maybe you can also explain for everybody that when, after the Pluto flyby, the idea was, well, you know, we're going out further into the Kuiper belt. There may be an opportunity for another, you know, intersection, but it's not as though we can steer this spacecraft anywhere.
No.
We have limited fuel, so you kind of had to go into a look in a fairly narrow.
That's right. So we are hoping to do another flyby. That is by no means guaranteed, but we are going to try very, very hard. We've already crossed about half the Kuiper belt, so finding something, it was already very hard to find Ultima Thule itself. It took a great deal of dedicated time on the Hubble telescope. Yeah. So to find something in the next half of the Kuiper belt, it's going to be further away, it's probably going to be smaller. We really can't even invoke Hubble now to help us. And so the cameras on the spacecraft, which has this little, you know, piece of view in the sky, that basically captures about the space we can steer into, because we have a little bit of what's called hydrazine. It's the propellant on the spacecraft. And so we can steer a little bit, but we can only steer within a very narrow cone on the sky. And that cone is about the size of our camera's field of view. Right. So we'll be looking forward to see if there's anything that we might be able to have as a candidate for another flyby.
Yeah, yeah. Now, the Voyager missions, of course, didn't investigate anything nearly as far out, but in terms of where the spacecraft physically are, they're outside the boundaries of the Kuiper belt?
As I understand it, they are outside the Kuiper belt.
Outside the heliosphere?
They are outside the heliosphere. And by the way, New Horizons will never catch up.
Yeah.
The Voyagers had the benefit of flybys of Jupiter and Saturn, and in the case of Voyager 2, Uranus and Neptune as well. And each of those gives a little extra speed boost. With New Horizons only having passed, the only massive object it passed was Jupiter, it's always going to be traveling at 14 kilometers a second, and but that's slower than the Voyagers, and it will never catch up to them. But it will go on, you know, sailing off out into the galaxy forever. Yeah. And that's a fun concept to think about.
It could be our own Oumuamua in somebody else's solar system.
It's
someday.
A very small Oumuamua, but yes, it could be that.
Yes, fantastic. So before we dive back to Pluto and investigate that, do we have any questions that are coming in?
So one person, Sandra, has asked, how many of these snowball-like bodies have we seen?
Well, so out of the Kuiper belt, we have seen, well, 2 if you count both pieces, but there are objects that have fallen into the solar system from the Kuiper belt. For example, a lot of comets probably come from this zone of the solar system. And so we've seen what happens when you take an object like Ultima Thule and bake it for a few billion years by the sun. And you end up with something that often still has kind of 2 lobes, but it's been highly battered and highly modified by the sun. Yeah. So this is the only pristine piece of the solar system we've ever seen.
Now, but as far as snowballs are concerned,
and yeah, let's be clear about snowballs.
Yeah.
This is not water ice, probably. It's got a mixture of probably a variety of things, but and water ice is certainly going to be a component of it. But don't think of it entirely as a snowball.
I mean, I think what's happened is people have referred to it as a snowman because it had these like
that's maybe
2
a little bit
snowman-like shapes, and you know, some of the pictures make it look whitish, which it isn't. But
exactly.
But however, comets we think are largely dirty snowballs.
Yes, that's right. Yeah. That's right.
Okay, great question. Any other questions?
No other questions right now.
All right. So Pluto.
Oh yeah.
So that was amazing.
So now Pluto. Okay. Pluto.
Actually, so before you talk about Pluto, talk about the hazard avoidance team and what your mission is as part of the overall science team and mission team.
Right. Well, so I'm just a co-investigator, which means I'm a member of the science team, and so the fun really began a few days before New Year's Eve, because that's when we just were starting to resolve this object and learn more about it than we had learned
on the way
ever before.
Right.
But one of the things about flying into the unknown, which is literally what we were doing, is that we don't know what the environment around this object is. It could have satellites. It could have the dust cloud. It could have rings.
And by satellites here, we mean its own little moons.
Its own little moons.
Little
yes,
spacecraft.
natural. Yes, a third little object going around the central object. So all those things could potentially create hazard. And if you're flying along at 15 kilometers a second and something the size of a pea hits the spacecraft, well, if it hits the wrong piece of the spacecraft, like a critical cable or a CPU or anything like that, it would be irreparable damage, the spacecraft would essentially be lost completely, and that means the entire flyby would be lost, because as we noted, all this data is on the spacecraft right now, and if it had not survived the flyby, we couldn't wait the 20 months to get all the data down. It would just all be gone.
Yeah.
So, so you lose almost everything if you don't lose half of everything. You lose everything if you are damaged at the flyby. So, so my team started work about 18 months ago. About a dozen scientists doing different kinds of image analysis and numerical modeling to just be prepared for whatever we saw as we approached. And our team then arrived in Maryland right after Thanksgiving, and I don't want to sound biblical, but I was gone for 40 days and 40 nights.
You are biblical, Mark.
Because the hazard team basically was in charge of looking at image after image after image, looking for any sign of any danger, and then we had the alternative to fly to an alternative further distance from Ultima Thule itself if we had seen any dangers that were in close.
So it's basically your team was going to determine how close in you could get to the lower limit.
Well, we had two choices because
they
they could only plan 2 possible flybys.
I see.
It would be impractical to do more than that. But so we had the 2 options, and it was our job to recommend to the project management whether it was safe or not to do the closer one, because the closer one, of course, gives you better data.
Yeah.
And in the end, we didn't find any risks, and so so we flew the prime trajectory, the closer one, and that's what we're going to be seeing the data from now. But just to sort of emphasize, you know, working on the hazard team is kind of monotonous. I mean, we spent 40 days and 40 nights finding nothing.
Looking at pictures.
And that's not in the nature of scientists to particularly enjoy finding nothing. But so kind of to relieve the tension and to just break things up, like our team leader, our team principal investigator, Alan Stern, came with this great idea. And so we had fun. We had like hazard helmets, and you can see our logo, which says "Know before you go," and it's got a silhouette of the spacecraft, and then there's this black silhouette of a dragon off to the side, because a dragon was something that we might have considered to be hazardous if we had found one, which I guess was not very likely.
And
so
by the
anyway,
way,
so there are many pictures of us with our hazard team hats and so on. But
one
it's
of those
just,
pictures is on our website.
Of course it is, and
so
it's
check that out.
It's
a fun shot of the whole
picture.
team.
That's right. Yes.
But so, however, I mean, it might have been, you know, kind of tedious work, but this is an example where the null result is a nice result.
Yeah,
it means
yeah,
absolutely,
absolutely. Nobody was sad that we didn't see anything, but it's just it's one of those. It's a dirty job, but somebody's got to do it. It's you know, we had fun. We had a great time actually doing this. And even when you don't find anything, you learn so much by not finding stuff. We've learned everybody's shared their different ways of doing data processing and so on. It's a great learning experience for all of the scientists who were involved.
Well, you led the same effort for the Pluto flyby, and you did find stuff. Actually, you found 2 moons.
To clarify, so that we discovered and discovered Kerberos and Styx, 2 small moons of Pluto. That was actually using Hubble. That was not during the hazard operations, but it was partly because of the discoveries of, at that point, there were 5 moons of Pluto, and that's as many as we found total, but we didn't know. We were thinking, if we found 5, what else is out there? And so that's when the hazard team first formed to handle the Pluto flyby, where they had a number of different alternative trajectories based on what they might see. And I was actually the deputy lead for that effort, and then took over for the Ultima Thule flyby. But once again, it was a 4 to 6 week period of finding nothing. But you make the best of it, and we all had a good time, even though we worked very hard, and we feel confident that we've made a good contribution to the flyby.
Yeah. Well, mission control for both the Pluto flyby and Ultima Thule was at the Applied Physics Laboratory at Johns Hopkins University. And so for the Pluto flyby, as Mark says, so the moons, Kerberos and Styx, had already been found. Mark is noted as the discoverer of those moons. And so the band, Styx, naturally thought, oh, they're naming a moon after us, which of course isn't quite true. I think they both have in common that they were going back to Greek mythology for the name Styx. But the band showed up at the Applied Physics Lab. They wanted to meet Mark, because they wanted to meet the guy who found the moon and named it Styx, or led the project to name it Styx. And they had their photograph taken with Mark, which was on NASA's homepage for a couple of weeks.
If you Google Styx meets Styx, to this day, you will see an image of five 5 people, 4 of which are rock stars and 1 of which isn't, and it's not very hard to tell the difference.
Yeah, but you're a different kind of rock star. I mean, it's literally a
very
rock
flattering.
star,
Thank
right?
you, Bill. That was a good segue.
And I will tell you that when Mark came back in July of 2015, or maybe it was August, because you were there for a while, I remember asking Mark, I said, so who was more excited about meeting who? And I remember to this day Mark's answer, which was, well, let me put it this way, they asked for my autograph. So I thought that's pretty cool.
They're actually great guys.
Yeah.
And they've given us backstage passes to concerts in the Bay Area.
Yeah.
It's been
a lot of fun.
It's been a big give and take relationship.
Absolutely,
Yes.
absolutely. They did a call out for you when they played at Shoreline.
They did. That
which
was
awesome.
That doesn't happen to most scientists very often.
That's
to
right,
get
that's right.
shout out in front of 20,000 people.
Yeah, that's pretty cool. Well deserved. All right, so talk about some of the stuff we learned on the Pluto flyby, because that, I mean, the images from that are
Yeah,
just
that's a kind of
breathtaking.
overwhelming still experience. So it's a, who would have thought that an object that far out, that cold in the solar system would have active glaciers? Those glaciers are not made of water ice like they are on Earth. They're made of slow flowing, muddy kind of a nitrogen ice. But it has mountains that are made of water ice, and they are essentially floating in this, muddy, pretty solid at those temperatures, but nitrogen and methane and ammonia and some of these other things. It's got cloud layers, which we knew there was a thin atmosphere to Pluto, but we never knew that it was literally layers of
So
clouds.
stratified, like
Stratified,
wow.
which means that it's acting more like weather and more like climate than it is like just a fuzzy. I mean, the moon has a very, very thin atmosphere that is just stuff floating away. At Pluto, it's not just floating away because it's forming these layers.
Interesting.
we
And yet
s-
Pluto is, how, compare it to the size of the moon?
Oh, it's smaller than
Smaller,
the moon, quite a
right?
bit smaller. Yes.
So it's interesting that it has this
Yes,
atmosphere.
and the first image we got that was a close-up of Pluto showed this big white field with not a single crater in it.
Yeah.
Now, the idea that an object, a big field, would have no craters at all, which means it's very young, probably
It's active.
It's very active. So there's a lot of active geology. There were also extinct volcanoes that we saw. It was just a marvelous cornucopia of different kinds of geological features all mixed together.
Yeah.
You just don't expect that, and it was a great surprise, and everybody's still spending a lot of time trying to make sense out of that Pluto data set.
Now, I understand as well that the mountains, the water ice mountains, they say that the water is like as the hardness of rock. It's just so cold and maybe so old as well. Can you?
That's
can you
right.
comment
I
on
mean,
that?
I'm not a geologist, so
Yeah.
one of the things I found interesting, and they taught me this, is just how hard water ice is when you get to these temperatures, which are like 50 Kelvin, something like that, 50 degrees or so above absolute zero. And things like the other things that it might have been, like ammonia ice or other kinds of things such as that, those are not strong enough to hold up a mountain. So
Yeah.
the fact that we saw mountains that are kilometers high meant for sure that they had to be made of ice, because there was no other compound in the system that was strong enough to hold up a mountain.
And how high did we get the altitude of some of those peaks?
I think they were up to like, I would have to check the number to be precise, but it was kilometers.
It was kilometers high.
Yeah.
Amazing.
These are big. These are not small mountains. If you saw them on Earth, you would call that a mountain.
Yeah. And by the way, in terms of some of the images from Pluto, as well as some wonderful animations that have been put together simulating a flyover of the surface of Pluto, NOVA, the PBS program, NOVA, just did a special that aired almost like a day or two after the flyby.
It aired on January 2nd, which
Yeah.
is amazing, because the first data we got was the first good data we got, the day we found out it was this, bilobed sphere,
Right.
contact binary. We got that data late in the day on the 1st, the team did.
Yeah.
The team had to spend the night making sense of what this thing is and how it worked and all. And then we had our press conference at 2 p.m. on the 2nd. That's when we showed
You were
the
on that-
images.
you were in that
No, I
press
was on the
conference?
3rd.
Oh, you were on the 3rd.
But on the 2nd, we showed these images for the first time, and that evening, NOVA had their broadcast.
Yeah.
So they had prepared most of it in advance. I think I show up for
You're in there in the beginning,
3 or 4 seconds
5 minutes
myself. But then the last few minutes, they actually devote to the real great science that had just been delivered
coming.
that day.
It's extraordinary that they had like really up to the minute content on that program. Wonderful program. Check it out. Yeah, Mark's at about the 5-minute 35-second mark, and you can see him
But who's
talking about
counting?
the horizon. Yeah, but who's counting? Me. But anyway, you have some images you'd like to share?
Well, so these are just kind of some images of the flyby itself, just to give you the sense of what it was like to be there. Because the images that you've seen, I think, speak for themselves, and we've already talked about them quite a bit. There are not a large number of images yet. We'll be getting some more very soon, as I understand it. But so here is the first day of operations of the hazard team.
This is not
we
a
had
drill.
gone through so many practice sessions that I felt I had to start off just by saying this is not a drill. Which, if you was actually, I can animate things. It was like this flashing neon sign thing that I came up with just for fun.
Get their attention.
This is what a lot of our images look like, and that looks rather boring. But that is actually, it's basically a close-up of a point as seen by our camera. But we were studying that point very, very closely. Does it have any weird shape that might suggest a close satellite? We were pushing very, very far into the background to see if there's anything that might be another satellite or ring, and so on. And so this was just kind of a day in the process. Here we are celebrating at the final end, where there's some members of the hazard team, and that's Alan Stern giving me the thumbs up.
That's
because
Alan.
we have decided at that point that we're going to fly the prime trajectory, the closer trajectory.
That's the shot.
This is a great fun
Yeah.
shot with a lot of little Easter eggs in it that I could love to talk about, but we probably don't have time.
Point out a couple of them anyway.
Well, let's see if I can zoom in. Here, Dave Kaufman was one of our numerical integrators, and by the way, so those screens show some of the models for what dust would do in orbit around Ultima Thule, but he wrote this little kind of like a C program that says basically, if hazard equals null, print go go go, and so that was his little joke.
That's great.
You can see over here. Let's see. I'll go in again. So there's me just saying what the sign says, we're done. Over here you can see the words Galileo Figaro Magnifico, because we have all seen the recent Bohemian Rhapsody movie.
Okay.
So you can see the different people showing their different image analysis techniques, and some of the science, the management and other members of the science team as well. Here's the Ann Burbisher holding one of the models we had. So even before we had seen this thing as a contact binary, we had some clues that might be what it's shaped like. And so anyway, this is just an indication of a team working very hard, but also having a bit of fun. And of course, we're all wearing our helmets.
And this is, so just to give them a sense of scale, this is just the hazard avoidance team. And
Yes.
there's a whole, there's the navigation team.
Yeah, there's about 30 scientists. So this is a small subset of the science team, but then in addition to that, we have mission operations, which is another 30 to 40 people.
I love that the mission operations manager was a woman and they called her Mom.
Mom, mission operations manager,
Yeah.
Alice Bowman, yes.
And did an extraordinary job from all that I understand.
Oh, she's an extraordinary person.
Yeah, that's
Yes.
great.
And
So New Horizons has a mom for all you moms out there.
So after the
Oh, this is great.
hazard operations were finished, the team gave me the Star Trek cap. So this is Captain James T. Kirk having a bad day. That's my best way to describe it. John Spencer in the science officer's shirt. He did the science. He was the science lead for planning the flyby, and Alan Stern there in the middle. And I had to practice to get my hand to go like
Was
that.
Alan unable to do this? Is that basically?
Well,
what's
no, he's
happening?
doing a 9. You see, he's
I see.
a 9-planet guy.
I see.
So we're doing Live Long and Prosper, and he's doing 9.
So, all right, he was out of script.
Right.
Off script.
And just some other, here's some pictures showing, this is, so one of the things I did after we got the good images was trying to figure out how it rotates and figuring out how it's oriented on the sky and so on. So here's one of the pictures from the, probably the January 1st when we're trying to make sense out of this particular image.
Oh, and this is why people think of it as a snowman, because I mean, if you were a kid making a snowman, that's almost the exact proportions you would use.
Yes, exactly.
That's pretty fun.
So, just, that's kind of what it was like to be there.
That's
it was
great.
just an extraordinary experience.
Yeah. Well, and so this is another indication of the work we do at the SETI Institute and our involvement with so many NASA science missions. You've heard us talking about the Kepler mission, where we've been very much involved in Cassini and of course New Horizons. So, it's just another example of the breadth of research we're engaged in at the Institute. We do have a couple more questions, so
Sure.
let me throw those at you. This is a good one from Spencer. What science will New Horizons be able to perform as it is leaving the heliosphere or passing through the heliosphere and beyond? What else might it be able to do?
Yeah, so we're already doing some really interesting science in addition, where although we're only going to be close to this one object and maybe if we're lucky one more, there are a lot of Kuiper Belt objects and they're scattered off in all directions. But from Earth, you can only see them with the sun basically shining over your shoulder.
Yeah.
So here we're out in the Kuiper Belt, so we can see them from different directions. We also have time, which is something, if you're studying the Kuiper Belt from Earth, you got to get time on a telescope. You can only look at night.
Right.
You have to, compete against people who want to do all kinds of other science. So we can, for example, pick one distant KBO and just wait and see how it rotates and see what it's doing in that regard. So we're doing remote observing of more distant Kuiper Belt objects. We took a break in order to do the flyby, of course, but we've been doing that before and we'll be doing that after.
Yeah. Do you have any images pointing the camera back towards the sun just to see how small
we would
the
love
sun
to do
is
that.
from-
There was a famous picture from Voyager that was
Sure.
called the Solar System Portrait. We can't even at this distance, we can't point the camera toward the sun without damaging the camera.
Oh, so you'd hit the saturation.
So it may well be that when we're significantly further away, we could do some kind of a solar system portrait.
Yeah.
Or we could do one that sort of mosaics around the sun without actually looking at the sun, which is what Voyager did.
Yeah.
But there's talk of that, but there's no formal plans right now.
Sure. Interesting. Another question from Owls, I'm guessing this says. At what point will you be unable to get images simply because the spacecraft is too far out?
Yeah, so there's a couple things working against us. One is we've got a 20-watt transmitter, and so on a dish about this big, and so it takes about an hour now to send an image down to Earth, where on Earth it's received by a 100-foot wide dedicated radio dish.
Right.
So it will take longer and longer to get data down. But the other thing is we are generating our power with a plutonium, thermal plutonium, essentially a pile of plutonium that gets hot, and we use the heat to generate electricity. And so that has a half-life that means probably we've got another 10 years, maybe a little beyond that. If we start shutting off some instruments relative to others, we might be able to push that a little bit further. But eventually we'll just run out of power on the spacecraft.
So you think it'll be power more than transmit power that will?
It will probably be the so even when you get further away and you've got less power, you can turn off some instruments to save power and then put the 20 watts into the transmitter.
Yeah.
So I think the main issue will just be that eventually we run out of power.
Okay, interesting.
And that's 10 plus years
10
away.
plus years.
Yeah.
Final question coming from Phil. Is there any way to bend space-time to send signals and messages faster?
That's a good relativity question.
That's
now,
right.
I'm not sure that, you got to consider that, general relativity is an amazing topic, but it is most prevalent, most observable on sort of cosmological distance scales, like distances to galaxies, around black holes, and so on. We are still right at home. 4 billion miles sounds like a long way to go, and it is. But it's 4 light years to the nearest star. It's what is it, 1 million something parsecs to, or I forget the number of parsecs. Someone will have to correct me.
Yeah.
To the nearest galaxy. So on the scales that we're talking about, probably general relativity and some of those cool aspects of very up-to-date cosmological and modern science, modern physics aren't going to help us.
Yeah. If you think about exploring our own galaxy, probably let alone the universe, I guess traveling to the edge of our solar system is equivalent of being at home, trying to explore planet Earth and essentially opening the door and stepping onto the porch.
Yeah.
Right.
Yeah. Well, no,
Maybe a little
it's probably putting a little piece of your big toe out past the door.
Past the door jamb.
Yeah. We have not gone very far. There's a long way to go.
Yeah. So as impressive and distant as this is, it's a small little step. So finally, and then I want to acknowledge friends we have from all the different parts of our planet that they're tuning in from. Just a little word about the project of naming Ultima Thule, which again you led and the Institute led.
We had a public campaign to name it, and the name is it's a sort of a mixture of Greek and Roman mythology. Thule was 2,300 years ago. I Pythias, I forget the name of the Greek navigator, left the Mediterranean, went off, and probably found, it might have been Iceland, it might have been Norway, but that was called Thule, the most distant, coldest place that he had ever seen, or any of the Greeks had ever seen. And then, so that's Thule is Greek, but then going into cartography in the Middle Ages, and actually before that, people were talking about, well, there are places beyond that, and so Ultima simply means beyond. Now that's Latin, but so it's a mixture of Latin and Greek, but beyond Thule means, essentially it's come to mean in a lot of literature and poetry and so on, means just beyond the limits of the known world.
Yeah.
And that was a beautiful metaphor for what we're doing, and that was the name that...
So that was one of the entries that somebody put in, is that right?
Or a peanut, or there were many other
thousands of entries you got, right?
Oh, it was we had nominations numbered in the 30,000 or something like that. We had to whittle it down quite a bit to come up with a list that people could vote on.
Right. That was great project. All right. Well, listen. I want to thank you so much for sharing your story with us. It's awesome. So, and I think we should have some hearts and thumbs up for Mark and the Hazard Avoidance team, for Pluto, now also for Ultima Thule. I love this, that you've got this sort of dual purpose model here.
It's who would have thought?
It doesn't hurt, even if you get hit with it.
Yes,
but,
suitable for young children. But
absolutely.
I don't make money on it, so I can say it's kind of a cute little toy.
It's very cute. But anyway, fantastic mission, and thanks for talking about that with us. And we'll have a story, more of a story about this mission and Mark's involvement with the whole New Horizons project in our upcoming edition of Explore, which is the Institute's magazine. So keep visiting our website at SETI.org, and you'll stay on top of when that's coming later in the spring. Meanwhile, I want to thank our visitors from Edinburgh, from Missouri, from Illinois, Indiana, from Sydney, Australia, from Ashkelon in Israel, from Finland, from Kurdistan, Switzerland, my own other hometown or country, from London, from Ireland, from Brazil, Germany, Belgium, Puerto Rico, Quebec, Argentina, Christchurch, New Zealand, Kansas City, Missouri. So even Kansas City, they've taken time out from their Super Bowl contending Chiefs to watch us. So greetings to everybody. Thanks so much for tuning in. Don't forget to visit SETI.org and stay on top of what we're doing, and sign up to get our newsletter, which allows you to get cool stories like Mark's work and that of his colleagues. And Mark, thanks again so much.
Thanks, Bill.
All right. And
Thank you,
I guess
everybody.
we'll send out some relevant links to folks so they can see some of the stuff we've been talking about, and definitely check out that NOVA program. Okay, everybody, from the SETI Institute in Mountain View, thanks very much for joining us, and we'll see you next time.
Thank you.